Hello and good morning. My name is Bhattarai and I'm an undergraduate student at New York University, Abu Dhabi. And today I'll be presenting our research on the relationship between open source code repositories and the scientific impact of research papers in computer science. First, I'd like to start by talking about the reproducibility crisis in computer science. There's an increasingly concerning trend of a lot of the work being published today without appropriate concern for transparency and reproducibility. This issue has been picked up by media outside of traditional academic circles, as you can see by the two headlines shown in the slide. The one on the left is from Vox, the one on the right is from the Technology Review. Transparency in computer science is usually associated with the inclusion of code or data alongside a publication, and these are usually done using online hosting sites like GitHub or GitLab. It has been argued that making a work more transparent and reproducible are not only good research practices, but also make a work more easier to build off and are more likely to have greater scientific impact, since future researchers can easily build off a more reproducible work. So with this overview, our research team wanted to use a bibliometric approach to quantitatively study the relationship between academic transparency and scientific impact in computer science. We wanted to know if efforts towards transparency would be rewarded with greater scientific impact, and what, if any, predictions could be made about a paper's success solely from engagement features and repository attributes from these online repositories. So we started our research by the data collection. We collected the data of papers and repositories from various online sources. For papers, we limited ourselves to the top 8 CS conferences over the last 10 years. We use DBLP, which is a free online and quite extensive bibliography of computer science. And DBLP got us a link to each paper. So from this link, we downloaded a PDF version of each paper, which we will later use for document mining. This graph here shows the distribution of the papers we collected over the last 10 years across the 8 conferences. You might be familiar with most of these conferences. They're some of the highest impact publication venues in CS over the last 10 years. So since DBLP did not have any citation data, we decided to use Google Scholar to get citation data for each paper. Google Scholar was chosen instead of other bibliographic sources because it has an extensively larger coverage. It indexes papers from multiple languages, for example. We query Google Scholar using the paper title and venue, and to prevent any mismatch, we restrict results to the paper's year of publication. We get the information for the title, the venue, and the publication year from DBLP. One of the fundamental issues with working with citations is that they are cumulative. A paper is more likely to get cited over time. So if you want to do any analysis that depends upon these citation values, it's unfair to compare a paper from 2011 to a paper from 2019, because a paper from 2011 is more likely to accrue more citations just because it was published earlier. So in this work, all analysis we do, we separate papers by its year of publication. Finally, we also label papers as highly cited if they are within the top 10% of papers by citation count in its year of publication. This will be used later on for things like classification and further analysis. But basically, we distribute a paper as highly cited or lowly cited. So this is a sort of a citation distribution of all the papers in our dataset. As you can see, the distribution follows a power law, and it is consistent with previous studies of citation distribution. Right. So the other main part of our data collection process was getting links to these online repositories. But when we talk about a publications or a papers repository, we mean a open source resource that was released before or concurrently with a publication. Early on in our research process, we realized that the most exhaustive way to obtain these links is by searching within the text of a publication. So most of the time, if you're including a link to an external hosting site, an external repository somewhere, you're either going to include it as a footnote or somewhere within the paper itself. And a preliminary analysis showed that most of these repositories were hosted using GitHub. So for data consistency, we decided to stick to GitHub. Links to these GitHub repositories were searched within the PDF version of these papers using regular expressions. However, we did realize a big problem could happen if we were to just rely on simple regex matching. There could be, I mean, there were a lot of situations where multiple papers were being associated with one repository and vice versa. So to ensure the optimal matching between a repository and its paper, we decided to maintain a one-to-one relationship between papers and repos. To do so, we decided to use some simple heuristics. So firstly, if multiple papers are linked to a repository, we pick the paper with the oldest publication date. The rationale of doing so is that the repository should be associated to the paper that shared it first. This simple heuristic eliminated most cases where the same repository is included in multiple papers. So for example, if the same set of authors include the same repository in multiple papers, or if a paper is citing a repository that it used in its own research work, which is much more common. Secondly, and this was much more rare, but if multiple repos are linked to a paper, we pick the most popular repository. So an example of this case could be where the same paper is releasing two different repositories, one for the code, one for the data. And our decision to use the most popular repository lies on the fact that we want to make sure that the most popular repository is representative of a paper's impact. At the end of this process, not every paper is guaranteed to have a GitHub repo. The most simple reason why this happens is because there is no GitHub links in the paper itself. But another reason is because it's simply citing a GitHub repo and not linking to its own GitHub repo. Right. So after we extracted the GitHub links from the paper, the next step was to use the GitHub API to obtain repository attributes. First, we collected static attributes. So these are simple one-dimensional numbers that sort of like relate to certain features of the repositories. And this is stuff like stars, forks, subscribers, etc. Furthermore, alongside these simple attributes, GitHub also lets you collect the time-stamped markers for when someone stars a repository. So starting is a very common feature of GitHub. It's mostly used to bookmark repositories for future use. Basically using the GitHub API, we collected all the times at which a GitHub repository is getting started. We then use this data to create a time series for the stars, which we call the stars time series. And this stars time series represents the temporal evolution of the repository, and it's also a good representation of how engagement, external engagement to the repository is fluctuating through time. So with that data collection out of the way, we decided to look at three major research questions. First question is for all research papers, and it's about the effect of including a GitHub repo on the citations of a paper. We will quantify the statistical difference between papers with and without a repo. The other two questions are about the relationship between repository attributes and citations. So we will only be including papers with a GitHub repo. The second research question is about the difference in repository attributes between highly and lowly cited papers. So, for instance, does the distribution of stars in a highly cited paper differ from the distribution of stars in a lowly cited paper? And finally, we'll be training a classifier to see if repository attributes themselves can predict whether a paper is highly or lowly cited. The first two research questions involve quantifying the statistical difference between two distributions. So we'll be using a fairly common method, which is the Mann-Whitney test, to signify the statistical difference between the two distributions. Additionally, we do not want to just rely on the Mann-Whitney test and the p-values, and we actually want to compute the magnitude of the differences between the two distributions. So we'll be using Cliff's delta as a measure of the effect size between the two distributions. Cliff's delta is great because it doesn't make any implicit assumptions about the spread, shape of the distribution, and it also doesn't need independence assumptions. So this table here shows the difference in the citation distributions between papers with and without a repository. This is for the first research question. As you can see from the p-values here, there's not a statistically significant difference in citation distributions between 2010 and 2013. This is most likely because there are very few papers with a repository. But if you look after 2014, we find a statistically significant difference. The p-values are significantly low for every year. And we also note that for these years, the value of delta is positive, which means that there is a first of all a significant difference in the citation distribution for papers without a repository, but also on average the number of citations for a paper with a repository is higher than for a paper without a repository. So this leads us to our first result, which is that transparent papers are more likely to be cited, and we reach this conclusion through statistically significant difference in citation distributions, which we have obtained for every year after 2014. Now, for the second research questions, we drop all papers without a repository to understand the relationship between citations and repository attributes. We also exclude years before 2015 because there are not enough papers with a repository before 2015. This table here shows the Pearson correlation, which is the row, and the Cliffs delta. The Pearson correlation measures the simple linear correlation between raw citation values and the raw value of these repository attributes, while the Cliffs delta is similar to before. It's a measure of the effect size, measuring the difference in the distribution of the repository attributes between highly and lowly cited papers. The statistically significant values are bolded, and from a cursory look at the table, you might have noticed that only 4 repository attributes are statistically significant. So these are stars, subscribers, forks, and issues. And this significance is consistent across all the years from 2015 to 2019. Also, please note that the value of the Pearson correlation as well as Cliffs delta is positive, which means that papers with a higher impact are more likely to have higher values of these repository attributes. This leads us to our second result, which shows that high impact papers have active repositories. So the number of stars, the number of issues in these repositories are generally higher for highly cited papers than for lowly cited papers. Finally, for our third research question, we train a classifier to predict whether a paper is likely to be highly cited solely from 4 significant repository attributes that we found from the previous question. We train a logistical regression model and an SVM, and the results of this are present in the paper here. Additionally, alongside these 4 repository attributes, since we also have time series data, we also train a time series based classifier. We use KNN as our classifier of choice. Additionally, alongside just vanilla KNN, we also try a hybrid cluster then classify framework, where we first separate the time series into separate clusters, and then for each cluster we train a separate KNN model. We use 2 clustering methods, k-means and k-shape. Looking at the table, we can see that for 2015 to 2017, KNN plus k-shape seems to be giving the best performance, and the performance for these time series data seems to decrease as the years move on. It gets progressively worse from 2015 to 2019. This is most likely because of the fact that time series get shorter as time moves on, so there's less data in them, so they can make their predictions are less reliable just because they have less data in them. But logistical regression seems to do a good job in separating between highly and lowly cited papers in 2018 and 2019. So we reached our third result, which is by using a combination of repository attributes and time series data, we can predict if a paper is highly or lowly cited. This is the end of our presentation. And just to summarize, our results indicate that computer science research papers that make an effort towards transparency and reproducibility by making available an open source repository at publication are more likely to be cited within just a single year of publication. When considering only papers that have repositories, user activity in these repositories is highly correlated and predictive of high impact papers. We hope our work provides evidence and impetus for the necessity of transparency and reproducibility in computer science research. Thank you for listening to the presentation, and I hope you have a great day.